Okay, so last class we were discussing chevron plot. So this is what we were looking at. So if you're trying to look at the kinetics of a folding experiment, so this is say your y axis is the natural log of k observed, the observed rate constant, and this is your concentration of denaturant on the x axis. And then what we had was like this. Say we have it's coming from here. So this is the unfolding arm and this is the folding arm. I'll just label those really quick. Okay. The points where they cross, what is that point known as? This is your CM, isn't it? Okay. And there were black dots. So these black dots are your experimental points, remember? Okay, these were experimental points, right? So this was what Ku and this was Kf. So remember what we had, what was ln Kf equal to? Kf H2O minus m Kf times concentration of D, isn't it, right? And then Ku was equal to Ku H2O plus m Ku times concentration of D, right? And then we discussed why they would be following these slopes, right? Okay. So that means if you go to a very high denaturant side, so for example if you are going to a very high denaturant side here, then that means the unfolding rate constant would be highest because you are already on the denatured side, it is easy to denature, right. Similarly for the folding, if you are going to go to the folded side, then what will happen is the folding rate constant would increase with decrease in concentration of denaturant, or would increase with, or rather would increase with decrease in concentration of denaturant, or decrease with increase in concentration of denaturant. Because when you increase the concentration of denaturant, you are on what? The unfolded side. When you decrease the concentration of denaturant, you are on the folded side. So that is why this is your low denaturant and this is your high denaturant. Okay. So this was your typical chevron plot. Guys, please go through this carefully, right. You have to be able to get used to chevron analysis if you would carry on biophysical studies of protein folding, because this is one of the ways where people look at what is happening to the transition state. Okay. Now from here what we said is that on the y axis we have K observed, and we said that K observed is equal to what? It's Ku plus K of f, right. It is a sum of both, and then we can take the natural log on both sides, then we can write K observed is equal to natural log of Ku plus Kf. I wrote this down last time, and now you can I will not write the next one down, but you can see what I can replace it with by. See Ku and look at Ku from this equation, right. So what is Ku equal to? Ku is equal to Ku H2O times e to the power m Ku D, right. And similarly what is Kf? Kf H2O times e to the minus m Kf T, and that is what we wrote down last time. Okay. Good. Now let us take some examples and see what happens, but before doing that, just let me tell you one thing you can also do is, if you are given these two equations, this equation for ln Kf and this equation for ln Ku, this is what I want you to figure out. I want you to figure out an expression. I wanted to figure out an expression for concentration of D, that means what is this 50%? Cm, right? This is what I wanted to figure out. I wanted to figure out an expression for Cm, which is the concentration of D at 50% denaturation, right. So, based on these two equations you are going to figure it out, right. This is a homework problem for you, right. So, this is a homework problem for you, please do that. Okay. Now, let us take a few examples. Let us consider a simple two state scenario. Okay. We are always talking about two state to keep matters very simple. So, we have a free energy profile. So, this is G for you. Okay. So, suppose I am as something like this. So, this is the folded state, this is the unfolded state, right, and this is your wild type. Remember, this is your wild type. Okay. Now, what you do is you do a mutation. You do a mutation and then this is how it changes. The free energy profile changes like this. Okay. So, then the red one is your mutant. So, the red one is a mutant and then this one is F prime, okay, the folded state of the mutant. Now, tell me, looking at this figure, what have you done? You have stabilized the native state, right, by introducing this mutation. Remember, mutation is also referred to as protein engineering. Okay, that means you are engineering some sort of stabilization or destabilization in the protein, or stability or stability or the reverse. But having done the native state, what you have done is, you can see from the figure the way it is drawn, you have not affected the transition state, neither have you affected the unfolded state. Okay. The only thing that is stabilized is the native state, that means the only free energy change is in the native state. Now, is the protein being stabilized or destabilized? What do you think? Stabilized. Why is it so? Barrier increases, right. That means barrier increases, and also what you can see is the absolute delta G between U and F also increases, right. So, both good. So, that means this protein should be more stable, the mutant should be more stable than the wild type, right. Now, let us go back to your old equation, K observed is equal to K u plus K of F, right. So, this remember K observed can be written as 1 by tau, and we said tau was tau relaxation or tau observed, whatever, K of u plus K of F. Okay. Now, think about this under highly unfolding conditions, that means highly denaturing conditions, where conditions are really unfolding type, that means high concentrations of denaturant, right. So, keep this figure in mind, and let us talk about, move to the next page, high concentration of denaturant. Okay. Now, under high concentration of denaturant, tell me this, which one would predominate? Would Ku predominate or would Kf predominate? Ku would predominate, right, because it is already on the denatured side. Okay. So, there now here I can write then Ku is much greater than Kf, is not it? If Ku is much greater than Kf, then what is K observed equal to? Ku, or 1 by tau is equal to Ku, is not it? Okay. So, similarly, if I would ever go to the highly non denaturing conditions, that means highly native like conditions, what would happen? For highly native like conditions, that means for low D, what would happen? Kf is much greater than Ku now, is not it, because we are already on the native side, and then K observed is equal to Kf, or 1 by tau is equal to Kf. Okay. Keep these things in mind, these things come in very handy. Okay. Are you guys clear up to this point? Right. Now, go back to the figure, and this is what I will ask you. What I will ask you is, how do you think the chevron plot is going to look like in this case? Tell me 2 very important things that are going to change in the chevron plot. Two very important things. What is the first one? Based on the difference in free energy, what is the first one that is going to change? Okay. Let's go ahead step by step, right? So suppose, let's draw the chevron plot. Okay. Suppose this is the one, so looks like a V, right? This is the one which is for the wild type, okay, where this is natural log of K observed, and this is the concentration of denaturant, and this corresponds to what? Cm, isn't it? So this is corresponding to Cm for wild type. Is it clear? Okay, very good. Now tell me, help me in drawing the chevron plot for the mutant. Tell me what would happen. Look at this. The first thing, because of the increase in stability of the mutant, what would happen to the Cm? Would it increase or decrease? It would increase, because you would need, because it is more stable, the mutant is more stable, you would need more denaturant to denature it. That means what would happen is this would shift to the right, higher denaturant, very good, that would be one. So this is how you go trying to analyze the chevron plot. The next is, which rate constant would be affected, and this you have to say, which rate constant would be affected? Ku? Would Kf be affected? See, in this case Kf is not affected. Why? Because you are coming from, when you are coming from U to F, the barrier has not changed, so Kf remains the same. But when you are going from F to U, what has changed? The barrier has changed. So what will happen now? Ku would change, because you are looking at an unfolding. Okay, now good. So Ku would change. How would it change? Give me a qualitative idea. Would Ku increase or would Ku decrease? Ku decrease. Why? Energy is higher. Okay, good. So then should the plot not be looking like this? Can I draw a plot like this? So this is Cm for mutant. Okay. So this is the chevron plot for the mutant, and this one is for the wild type. So is it clear how the chevron plot would change? So you can see one thing. The first one is the Cm has shifted by this amount. So this is your Cm shift, right? Because you have stabilized the mutant, stabilized the protein by introducing mutation. Now initially your K was here, now K has come down here. Why? Because Ku is decreasing. You have increased the barrier. So it has become harder for you to unfold as compared to the wild type. But also Kf, which is on this side, is not being affected at all, right? So that means Kf is not affected, but Ku is being affected. So this is one way of looking at it. At least this is what the picture is, the simplest picture you can draw based on the example we started with. Is everybody clear with the interpretation? Good. So now let us move on. Let us look at the second case. So this was example 1. Let us look at this example where this is G, okay. This is again F, this is again U. Wild type, we do a mutation. Now because of the mutation, this is what happens. Now, for you what has changed in this case? Has the U changed? No. Has the F changed? No. Has the TS changed? Yes. So, the barrier to folding or unfolding both have increased, right, okay, guys. So, then in this case how would my chevron plot look like? So, if I am trying to draw my chevron plot, okay, say if this is my initial chevron plot, this is my wild type, looks like a V, again this is ln k observed. Now, tell me how would the chevron plot look like? Good, both would decrease, right? Will Cm change? Cm will not change because stability has not changed. Stability is defined by what? The difference between the free folded and the unfolded state. Stability has not changed, but your free energy barrier has changed. So, this would be your mutant. Clear? So, that means both Ku and Kf are decreasing. In the previous case, Kf no effect, Ku decreased, but because of the increase in the free energy, whether in the forward direction or the reverse direction, whichever direction you are looking at, this is the picture. Clear? Is this example okay with you? So, in the exam, if you are given a free energy diagram, you should be able to draw a chevron plot, or if you are given a chevron plot, you should be able to interpret what changes you are having in a free energy diagram using this thing. Okay. Good. See, so that pretty much brings us to the end of our theory section, in the sense that these are the changes we look for if we are doing any experiments. Okay. Obviously, these kinetic these kinetic data are taken from experiments, right. Let us try to look at what experiments are. So, if you remember one thing, what I said was, if you are going to talk about protein kinetics, that means you have to follow the protein folding or unfolding as a function of time, and hence one of the major things of doing is you have to do whatever change you have to do it very fast, and then allow the protein to evolve or respond to that specific change. So, then this brings us to one of the most important topics of this course, which is protein folding kinetics, rapid mixing and relaxation techniques. So, we are going back to the slides now, right. So, what are the different techniques we are looking at? This we are going to go step by step. The first one is a rapid mixing technique, right. The first one is a rapid mixing technique. So, rapid mixing, as the name suggests, is that you have to mix two things very rapidly, as simple as that. Once you mix them very rapidly, what you got to make sure is that the protein does not unfold or fold or does not change too much while you are mixing, right. Sorry, that sound was too loud. Does not change too much while you are mixing, because if it changes too much, then there is no use following the kinetics. The protein has already changed to a huge extent. So, our goal is to try to mix it as fast as possible, okay. And what can we do for that? But before going into the actual technique, let me tell you what are the tools. I will just tell you the tools and then we will discuss those later. You would use to detect the changes. See, changes can mean many things, and one of the major things is an optical signal, right. Say either absorbance, fluorescence, circular diachroism, or IR, which is also an absorbance, the vibration spectroscopy, right. So, let us look at the next slide. This kind of summarizes the common detection methods. Methods means the tools. These are not the techniques, but the tools. The tools are, the first one is fluorescence. Okay. What can you probe? I am sure you guys know about this. Proteins have 3 intrinsic fluorescent probes. What are those? One is tryptophan, one is tyrosine, and the other one phenylalanine. Okay. So, you can see 2 of these are written, tryptophan and tyrosine. So, if you would ever look at the changes of the signal coming from these residues, when you go from either the unfolded to the folded state, the folded to the unfolded state, as a function of time you will be getting a kinetics. Okay. So, what do these what does the signal depend upon? It depends upon solvent shielding, quenching and all these things. So, these we will talk about later, but just for you to have the idea. The next one is ANS. ANS is a certain dye. ANS is the dye which combines or which adheres or binds to hydrophobic patches in proteins. So, you can actually look at the evolution of the fluorescence of ANS as a function of time and see how that happens. So, number 2, and then one thing we discussed at the very beginning of the class, which was FRET. That means, if you have 2 fluorophores, a donor and an acceptor, see when the protein is unfolded, because the protein is unfolded, these donors are very far apart from each other. Now, as the protein will fold, these two would come close. So, what essentially what you can do is, if you can look at the FRET signal and plot the FRET signal as a function of time, that will give you the kinetics. Okay. So, all these we will take individually. Another method is absorbance, UV visible, tryptophan, tyrosine, there are cofactors known as heme cofactors if you go for the heme proteins like myoglobin, porphyrin moieties and all these things. So, they have also their own absorbances, and these absorbances change as the proteins fold and unfold. So, you can also look at that, right. Next one is circular diachroism. Circular diachroism is essentially going to tell you about the changes in secondary and tertiary structure of the proteins. So, it does not matter which one you pick, whether it is a secondary structure or tertiary structure, you can plot certain changes in the secondary structure as a function of time again, whether the protein is folding or unfolding, and then again get the kinetic information, right. See, all these we will discuss, so do not worry. The last one is infrared. So, this is also an absorbance method. In the top we had absorbance which was UV vis, which is in the UV and the visible region. The last one is absorbance in the infrared. So, we are talking about vibrational spectroscopy, and proteins have very well developed vibrational bands. One of the most popular bands being known as an amide 1 band, right. And if you would ever look at the amide 1 band changing as the function of denaturation or refolding, then you can also plot the kinetics. And these are some of the most common tools or methods that people use to follow kinetics. Okay. So, having said that, let us look at our first technique. This technique is referred to as a stopped flow technique. So, as the technique tells you, stopped flow means you have to stop the flow somehow, right. So, this is what is done. Remember, we are talking about a rapid mixing technique, right. So, you have 2 syringes, right. So, you have 2 syringes, say this is syringe 1 and this is syringe 2, and there is also another syringe here, this is a stop syringe, say this is syringe 3. Okay. Now, what you do is, because you are going to have to do a rapid mixing, see your whole system or technique should be having a few components. One is, you should be able to mix 2 solutions very rapidly, number 1. Then you should be able to have a cell, that means a cell in the system where you can observe the protein unfolding or refolding. Then to observe that, you have to have a detector. So, you will be having a detector. Okay. That is essentially the principal components, and of and going into the details, you would be having many other things, but let us just stick to the very basics, the bare minimum basics, that is what we need to know. So, here what you do is, you are going to do a rapid mixing, right. So, what means is, say suppose I am looking at protein unfolding, so that means rather protein, say I am looking at protein refolding. Okay. So, this is R, sorry it looks like a V, this is R, it is protein refolding. So, what I am trying to do is this, what I am trying to do is, I am going to start with the protein which is already in a denatured state. See, I am going to start with the protein which is a denatured state, that means the protein has to be in a high concentration of denature. So, what I write here is protein plus high concentration of D. Okay. This is coming in one syringe, right, one of the syringes has this. Okay. Now, how can I bring the denaturing concentration down? The only way I can bring it down is if I mix it with a very low concentration of denaturant or essentially buffer. If I mix it with buffer, and depending upon the amount of buffer you are throwing in, the amount of dilution you are having, you would be having your final denaturant concentration. So, this one is say just buffer. Okay. Now, what you do is you take these two syringes, you push these two syringes together. So, one syringe has the protein with the high denaturant, the other one is going to have what? The protein in buffer, sorry, just the buffer, right. These two samples are there for you in the two syringes to start. Okay. Now, the technique or the instrument is so set up that if you click on a computer on the software, then these two syringes would be pushed together. The moment you push the two syringes together, that means you push these two together, right? You push these two together. The moment you push these two together, what will happen? These two would flow out, right? From one you have the protein and denaturation, the other one we have the buffer. Then what would happen is, you can see these places. So, this solution would come like this solution would come in this direction and they would mix, is not it? They would mix and then they would finally flow into this observation cell. Are you guys with me up till this point? Again, you have two syringes, remember you have to push these two syringes simultaneously. So, these are two syringes, you have to push these two syringes simultaneously like this, and because you are pushing these two syringes, the solutions are being thrown out. Then once they meet here, say once they meet here, this is the meeting point, the solutions mix. But remember, I told you the solutions have to be in a certain cuvette or a container, because if you are doing an adsorbance or whatever, you have to have a sample cell. So, this is the observation cell where the solution comes in. Okay. Are you clear up till this point? Right. Now, the next stage is, see, I have started mixing, is not it? But the technique is called a stopped flow. That means, you have started the flow, but you have to stop the flow now, because how long do you want it to mix, right. So, now what it does is, again there is a very nice thing, see the solution comes in, right. You can see here, this is belongs to syringe 3, okay. It is connected to syringe 3. So, what would happen is, the moment you mix and the solutions come in the observation cell where you have this connection to the syringe starts filling up, is not it, because the solutions are coming into that syringe, which is the stop syringe. Now, once the stop syringe starts filling up, what will happen is, you see this is being pushed back now, because initially the stop syringe are nothing. Now, you are pushing in solution, the mixed solutions, and the solution is coming in, and this one is being this plunger is being pushed back. Now, how far will it be pushed back? It will be pushed back until it hits this stopping block. The moment it hits the stopping block, what it does is, the stopping block says, okay, that is it, I have enough solution for me to do the measurement, because see, I cannot just do with any small volume of solution, I have to have that much solution with which I can reliably do a measurement. Okay. So, essentially what the stopping syringe tells you is that the stopping syringe is so designed that it should be having that much of, say, 300 microliters or 400 microliters of volume, which would come into the stopping syringe. When that comes in, the stopping syringe hits the stopping block asks it to stop. That means your mixing is done. Clear? Once the mixing is done, now what will you do? Your mixing is over. Your mixing is over means, what does it mean? Your mixing is over means that your protein, which started with a high concentration of denaturant, has mixed with buffer in a certain ratio, and it sees suddenly a very low concentration of denaturant, because you mixed it very fast. I will tell you how fast it is. You have mixed it very fast. Typically you can do this in order of millisecond or so. Okay? You can do this very fast, or few hundred microseconds. Once it is mixed, now depending upon the protein, because the protein now suddenly sees a very low concentration of denaturant, it understands that it has to unfold. So, it responds to that, sorry, it understands that it has to fold. So, it responds to that folding condition and then starts folding, and that change, whether it is in absorbance, whether it is in fluorescence, whether it is in IR, whether it is CD, that in secondary or tertiary structure, you measure as a function of time, and this technique is referred to as a stop flow method. Is it clear or not? Is the technique clear or not? Guys, have any doubts, let me know right now. So, you understand why it is called the stop flow, right? It is called the stop flow because you have to stop the mixing, and the mixing is stopped by what? The third syringe, which hits a stopping block. and that is where the name comes from, the stopped flow. That means you are stopping the flow. Only after you stop the flow are you ready to take your first measurement. Before this thing happens, that means before you are stopping the flow, you cannot do any measurement, right, because this instrument is not yet ready for you to collect a measurement, because the observation volume or observation cell is not yet prepared or not yet primed for a kinetic measurement. Is this clear or not? Any doubts? No doubts? Okay, fine. Think about it, but please do let me know if you have any doubts. Right? Here we are actually talking about techniques which are being used in present day research. There are quite a few people who have this stop flow technique, and they used it in various ways to monitor protein folding, if that is what they are interested in, or that is what the research is based on. Okay. Right. So, you can understand then this mixing has to be done rapidly, right, because I cannot just, you cannot just sit and just push these two syringes like this, right, and wait for ages, because by the time you push these two syringes, the protein has already changed. So, you have to do this mixing pretty fast. So, because you do this mixing pretty fast, this brings us to an important technique or important concept which is referred to as turbulent mixing, which is referred to as turbulent mixing. That means mixing is very turbulent, right. So, like turbulent weather is turbulent mixing. Now, turbulent mixing is characterized by a certain number. Do you know what number is that in viscosity? Reynolds number. Good. So, Reynolds number, that means the type of mixing you have, whether it is laminar, whether it is turbulent, is given by Reynolds number. The Reynolds number is given by rho times V times d over eta, okay, where rho is density in grams per centimeter cube, V is the velocity of flow, this is centimeter per second, d is the dimension of the flow cell, that means the tubes through which the solution flows, and lastly what is eta, can you say? The viscosity, which is in units of poise, right. So, there are 3 factors or rather 4 factors which would determine your final Reynolds number, and this Reynolds number for a turbulent flow, this Reynolds number R e has to be greater than 2000 for a cylindrical tube, Okay. So, then what it means is that if you have to have fast mixing, you have to have turbulent flow. Okay. That means you have to have a huge amount of pressure going in. Now, keep this in mind. What is the expression for pressure? What is pressure equal to? Force per unit area. So, now you understand. So, for people who like for soccer players or athletes, they have very pointed studs, right, spike boots, studs. Why are they pointed? They are pointed because at their point of pressure or at their point of contact with the ground, the pressure is really high. Why? Because the area is small. So, it is force per unit area. The same thing happens here. So, think about this. How can you increase, say for a defined flow rate, how can you increase the pressure? You can increase the pressure by decreasing the dimensions of the tubes, right. If the tube is this large, then obviously the pressure will be low. If the tube is this small, for the same flow rate or the same force you are putting in, the pressure would be high. But remember, you cannot. So, one of the ways you can say is this is Reynolds number. I can easily play with the dimensions, right, but then you cannot decrease the dimensions too much. You cannot decrease the dimensions too much, because if you decrease the dimensions too much, then your pressure would be so high that you might actually end up damaging the instrument. because pressures can be really high under those small dimensions, right. Okay. So, that is typically what is done, right. So, whatever rapid mixing technique you are using, it has to be based on turbulent flow, which is defined by your Reynolds number, and that is what the number tells you, right. That is what the number you are going to supposed to have. So, coming back to the slides again, let us look at another version of this. So, same thing you are looking at. I have taken it from this again, this is the same thing. So, here this is what I was saying, you see this drive, this block, you see this block. What does this block do? You see this block is uniformly connecting the two syringes. So, this instrument is so built for you that when you click on the software, what does it do is it pushes the block. The moment you push the block, what will happen? It will squeeze the solutions out of these two syringes, right. Now, this one is a mixing chamber, come say observation chamber, this is just a little different thing. See, this is your stopping syringe. At the behind the stopping syringe, you have another stopping block, isn't it. So, the stopping syringe can only move to this extent, it cannot move further, the block stops it, and then your actual data collection starts. So, guys, now you can understand one thing, there is a limitation to this instrument. What is the limitation? The limitation is, first of all, how fast a mixing you are doing, but not only that, the limitation is the moment the mixing is done, you are not being able to start the data collection. When are you starting the data collection? You are starting the data collection only when your observation cell has the required amount of or volume of solution, the stopping block has stopped the flow, only then are you starting to observe. Is it clear? So, that means there is a time delay between the moment you mix and the moment you start your data collection. During this time, you are not being able to observe any conformational events, right. Take it from me, during this time you are not being able to observe any conformational events, and because during this time you are not being able to observe any conformational events, this lag time between the mixing and your forced data point is referred to as the dead time. Okay. So, this brings us to the next topic. This lag, so what is the dead time? So, the dead time is the time delay or time lag between the completion of mixing and the first data point or time point of collection. This is the dead time, because this typically is dead for you, you cannot observe anything during this time. Okay. So, this is a limitation. Typically in stop flow apparatus, this dead time is of the order of 1 millisecond. You can even, I think, go to 500 to 600 microseconds. That means below 600 microseconds or 1 millisecond, depending upon the stop flow instrument, you cannot go, right, because 1 millisecond is typically the time which is a dead time, only after which the instrument allows you to start recording your data. Is this clear or not? So, this is typically what goes on, and that is one of the disadvantages of this stopped flow method, right. But then I will also come to another method, and I will tell you why stopped flow also has its own advantages, right. I will tell you that later. Okay. Now, one of the ways of trying to improve it is this. Obviously, you can improve your mixing efficiency, that is one, but that can also be improved here. The other thing is, see, remember in the stopped flow what we had was there was a third syringe which was stopping the flow. So, suppose you can say, okay, I want to do this, what I want to do is I would remove the third syringe. Instead, I would let the solution flow from the moment it mixes, and then I will observe it from the moment it starts flowing. That means, throughout the flow I will observe it, I will not stop its flow. Okay. That flow is referred to as continuous flow. So, that is the next technique which is referred to as a continuous flow technique. I will discuss that very soon. but just trying to make the connection between these two different methods. One is a stopped flow because it stops the flow, and the other one is a continuous flow because it never stops the flow, it allows the flow to go through. Okay. Now, before going over to the continuous flow, let me show you. So, this is the same thing. So now you understand, right? If I am going to observe protein refolding, that means protein folding, in one syringe I am going to have protein in high denaturing, in the other case I will be having buffer. Okay. If I am going to observe protein what unfolding, what would I have now? Low denaturant or no denaturant, that means protein in buffer in one syringe, in the other syringe I will be having a high concentration denaturant. Okay. Simple. So that means think about the chevron plot now. Depending upon what you want, if you have very high denaturant, you would get Ku. If you have low denaturant, you would get Kf, and that is how you start going ahead to build the chevron plot. Remember, chevron plot, when we are talking about that equation ln Ku is equal to ln Ku H2O plus mKo times concentration of D, that concentration of D was your what? Your final denaturant concentration. On the x axis, what you have is your denaturant concentration from 0 to 7 or 8 or 9, depending on what denaturant you are taking. So, if you are say if you are monitoring folding, say if you are monitoring folding, say that means you are going from the unfolded to the folded state, you can come back to different final denaturant concentrations. That means you can come back to 0.5, 1, 1.5 and so, and hence you get those data points for every denaturant concentration. The same thing happens for the Ku if you are going the other way around, and this is how you build a chevron plot. Guys, is it clear? This is how you actually construct a chevron plot, right? Okay. So, going ahead, I told you, right, we are going to look at a change. So, let us see what this change is. So, this is a protein, a certain protein, okay, and this we are looking at fluorescence. You see, it is looking at fluorescence. Now, this one is for your folded protein. This fluorescence is for your folded protein. Okay, this is a fluorescence spectrum typically of your folded protein. Okay, this is coming from a tryptophan, say. We will discuss this later, but just take it. There is an optical signal for you, fluorescence. Now, this protein might be having an intermediate, which is given by this dotted line. This is an intermediate I. But what you can observe is this one is your unfolded state, which is U, and this is F. Okay. Now, what is the difference in the fluorescence intensity between the folded and the unfolded state? Which one has more? Unfolded state has less, right? Folded state has more. So, what does it mean? What it means is, if you would be looking at a protein folding, that means this protein folding from a high denaturant concentration, and if you are going to look at the tryptophan signal, what would happen? Or if you are going to look at the fluorescence signal, what would happen? Would it increase or decrease? It would increase, right? Because unfolded state is low and then goes to the folded state. So, this is the change you are going to look at, and this is the change you are going to monitor as a function of time. You are with me, right? Okay. Now, let us look at an actual example. Okay. So, this example is the protein cytochrome C. Okay. All of you guys have heard about this protein cytochrome C? You must have, right? In the respiratory chain and all these things, the electron transfer, right? Now, the cytochrome C is primarily alpha helical. You can see this N is the N terminus and this C is the C terminus. Now, this is what is most important. You can see in the middle, this is a heme, right, and here this is your tryptophan W59, that is your tryptophan. That means that is tryptophan which is at position number 59 in the chain. Now, what happens is in the folded state, remember in the folded state, or before going there, the tryptophan and the heme, they constitute a FRET pair. That means the tryptophan is the donor and the heme is the acceptor. Okay, just take it from me for the time being. So, what will happen is, remember what I told you before, if they are very close to each other, then they are going to talk. That means tryptophan is going to transfer energy to the acceptor. If they are going to go far apart, then that energy transfer would decrease. So, you can understand when the protein is folded, tryp and heme, because they are very close, the tryp intensity would be very low, the fluorescence intensity. Why? Because it has transferred most of its energy to where? The heme. The moment you unfold it, because they are now moving far apart because of unfolding, what will happen is the tryptophan intensity would go on increasing. Now, this is just the reverse of what we just discussed. In the last one we just discussed that it should be the reverse, that in the folded state should be having a higher intensity, unfolded state lower, but that was not a heme protein. Now, this is a heme protein we are talking about. Okay. Now, see, this is what happens then. So, some facts about cytochrome C: it contains a single tryptophan residue, that is about 40 residues apart or along the chain from the heme moiety. Okay. In the unfolded state, tryp and heme are far apart in distance, and hence there is a weak quenching of tryp fluorescence, okay, by heme. In the native state, tryp emission is almost completely quenched, as tryp and heme are in very close proximity. The distance is about 2 nanometers or 20 angstroms, that is very close, and hence most of the energy from tryp is transferred to the heme. Okay. Good. So, now you can understand what will happen is that if you are going to follow a folding experiment, what would happen to the tryp intensity now? Would it increase or decrease? It would decrease. Why? Because in the folded state it has the lowest intensity, in the unfolded state it has the highest intensity, right. Okay. So, that is what you see here. So, then you look at the tryp intensity variation as a function of time. So, this is what you see now. Do not worry about the shape or the emission maxima of the figures, okay. Don't on the spectra, do not worry about that. This is what you just consider. In the unfolded state, the tryp has a very high intensity. In the folded state, the cytochrome C, the folded state has a very low tryp intensity. So, if you would monitor this change, this change in fluorescence, say delta F, delta FL, where FL is fluorescence, right. If you monitor this change as a function of time, you are getting your kinetics. Okay. That is what people have done, right, and that is what I am going to show you right now. Okay. So, look at this. This is a typical kinetics you are looking at. Now, do not worry about this burst phase first. Let me tell you what you are seeing. On the x axis, what do you have? You have time. On the y axis, what do you have? You have fluorescence, right. Now, see, there is something known as S infinity. Can you see there is something known as S infinity out here? What does S infinity mean? S is the signal at infinite time. What does that mean to you? What do you mean by infinite time? Huh? Reaction completed. Okay. So, tell me a thermodynamic term for infinite time. Equilibrium. Good, equilibrium. So, that means infinity means that after you have refolded the protein, you have allowed it to come to a certain point beyond which there will be no further change, because it has already reached equilibrium. So, S infinity refers to as infinite time. Infinite time is not necessarily that you sit there and wait for infinity, right, literally. You just wait for the reaction to over. What you see is that in 2 consecutive or 3 consecutive time points, there is not much of a change in fluorescence signal. That means, you know, whatever change has had to happen did happen. Okay. Good. Now, what is S0? Can someone tell me? If S infinity is monitoring the signal at infinite time, what is S0? Monitoring the intensity at time is equal to 0. Okay. Now, in a stop flow technique, what is the time 0? Tell me, when does your time 0 start? Yes, then when it hits the block, right. So, you can understand now, I have already told you, by the time you start looking at the first point, that means by the time you have hit the block or the syringe 3 has hit the block, that solution has already mixed and it is already aged. That means, it is already there for some time, during which you could not collect the data, but some changes already happened during that time. So, then your S0, that means your time 0 starts from when the stopping block hits the syringe 3, but that is not time 0 for the reaction, is it? The reaction has already started before. Your time 0 is defined by the instrument. Your time 0 is not defined by the reaction. The reaction time 0 is far earlier. The only reason your time 0 is later, because that is what the technique offers you. You cannot go faster than that. So, then you can understand So, now you can see this difference. What does this difference correspond to now? A certain time. What is the time? The dead time. So, this essentially is your corresponding to dead time. Why is it called the burst phase? It is called the burst phase because there is a certain burst in conformational change in the protein which you are not being able to collect. Burst happens always very fast, right, and because it is occurring so fast, much faster than when you can start collecting, it is called the burst phase with respect to your instrument. Is that clear? That is why it is called the burst phase. It comes in a burst, right. Now you can ask me, what is SU predicted, right? What is SU predicted? See, how can you get SU predicted?
When you pressed.
The moment you pressed. But then when the moment you pressed, right, you are not being able to collect, right. So, how will you get SU predicted? Tell me. Is there any other way? Okay, tell me. So, this is what we will end our class with. Let us not talk about SU predicted now. Let us talk about the signal at infinite time. Suppose you would predict the signal at infinite time. Okay, what would you do? You are not doing a kinetics. I am telling you, you are looking at an equilibrium situation where you are predicting the signal at infinite time. How would you predict the signal? Come on. Huh? No, but you are not doing a kinetic experiment. I am telling you that how would you predict your signal at infinite time? Come on guys, we have done this. Apart from kinetics, what have we done? Good, we have done thermodynamics. Now, suppose I am doing this change, suppose I am doing this change to a final concentration of 0.7 molar denaturant. This is guanine hydrochloride, I guess. But you always know, if you would do a transition, that means if you would do a denaturing transition of this protein cytochrome C as a function of guanine hydrochloride, you will be getting certain points, certain values of fluorescence as a function of denaturant. Do you remember this or not? This is thermodynamics. Remember these transitions, the sigmoidal transitions? One was thermal, the other one was what? Chemical. Now, from chemical it is equilibrium, that means that is infinite time. So, when you are doing it at equilibrium at each and every point, whether it is 0.5, 0.7, 1 molar guanine hydrochloride, you exactly know what your equilibrium value of fluorescence is in this case. So, you can always trace back and look at the predicted value and look at a ratio. I will talk about this more in the next class. Okay? So, that is how you can do, because you always have equilibrium experiments at your hand. Now, tell me, what about SU predicted? How would you do that? Huh? By extrapolation from where? Oh, I can. Extrapolation is only applied to linear graphs. Listen, one way is, if you are talking about SU predicted, that is time 0. Think about a negative time, that means before the mixing is actually started. What is it SU predicted? It should be equivalent to your thermodynamic variable or thermodynamic value at that high concentration of denaturant, like S infinity. The moment you mix it, you cannot see. What he said is right, you extrapolate. So, what you do is, your final denaturant concentration is varied, like say 1 molar, 0.7 molar, 0.5 molar, 1.5 molar. Okay? You draw these, I mean you have these kinetic traces. The circles are your points, data points, the black curve is an exponential fit, and then what you do is, you can see out here there is no data point out there. So, you can have different denaturing concentrations final, extrapolate the exponential thing, and then try to get S of u. Okay, that's one way of doing it, right? But it needs a series of experiments. Right, we'll stop here. I've already gone beyond time.